Students, in the previous video we have studied relations and its types. Today we are going to study important topic which is functions. So watch the video till the end. You already know that the function is a relation from one set to another. Say for example, if I have a function from set n to n defined as fx is equal to 2x, that means it will consist of elements like 2, 4, 6, 8 and so on. Important is now different types of function. A function f from set x to set y is defined to be 1, 1 or injective if the images of distinct elements of x under f are distinct. That means for x1, x2 belongs to x, f of x1 is equal to f of x2 should always imply that x1 is same as x2. Correct? You know, if f is a function from x to y, that means x is your domain, y is your range. So in this case, f of x1 is equal to f of x2, then it should always imply x1 is equal to x2. If a function is not 1, 1, it is called many 1. Now in very simple language to understand, a function is 1, 1 means no two different inputs should produce the same output. Now you can see the diagram. In the first case, the function fx, which is given by x plus 1. Why x plus 1? Minus 4 plus 1, minus 3, minus 2 plus 1, minus 1 and so on. This function is 1, 1. You can see over here the function is 1, 1. But suppose if you define the function gx as x square, it is not 1, 1. Why? Because f of x1 equal to f of x2, 16 equal to 16 will not. But how can you get 16? You can get 16 by squaring 4 and also by squaring minus 4. So f of x1 equal to f of x2 will not always imply that x1 and x2 are same. See the second diagram. You can see that if you are having, see, simple language, try to understand it without making it confusing. No two different inputs should produce the same output. Correct? In the first case, if you see here, the function is 1, 1. Correct? But in the second case, it is not 1, 1. Why it is not 1, 1? Because the output B is related to two inputs 1 and 2. So that cannot be the case. No two different inputs should produce the same output. So the second case, it is not 1, 1. Next type of function is the onto function. A function f from x to y is said to be onto or surjective if every element of y is the image of some element of x under f. That means for every y belongs to y, there should always exist an element x in x such that fx is equal to y. In simple language, every element in the range is hit by at least one element in the domain. Correct? That means if you have some element in the range, it should at least have one element in the domain. For example, the function fx is equal to x is onto because every real number y, there is a real number x such that fx is equal to y. Simple fx is equal to x, that is an example of onto function. If you see the diagrams over here, in the first case you can see that for every element in your range, that means for f, g, h, I, all the four elements, you have at least one element in your domain. Correct? But the second case is not so. Why? Because f, g and I, they have their pre-image in the domain. But over here h does not have any element in the domain in x. So the second case, it is not onto. Second diagram if you see, then over here also it should have what is the definition? Every element in the range is hit by at least one element. So A is hit by two elements, no problem. B by 3 and C 4. So every element in your range has some element in your domain. So it is onto. But the second case over here, you can see that E and F have no element in the domain. So it is not onto. Now, if a function f from x to y is 1, 1 and onto both, then it is called bijective. Correct? If it is both 1, 1 and onto. Now, let us take an example. See, this is a little bit confusing topic, so try to understand each and every example. Show that the function f from set of natural numbers n to n given by fx is equal to 2x is 1, 1, but it is not onto. But the function f from R to R given by the same definition fx is equal to 2x is 1, 1 and onto both. Let us check it out. In the first case, f is from n to n, f is 1, 1. Why? Because f of x1 is equal to f of x2 will always imply 2x1 equal to 2x2 will always imply x1 equal to x2. So it is 1, 1. But f is not onto. Why? For showing it is not onto, you can give one counter example. As for 1 belongs to n, there does not exist any x in n such that fx is equal to 2x which is equal to 1. That means that if I am having any element 1 in the, remember, this n is in your codomain or range. So if you are having any element 1 in your range, then there does not exist any element. Can you say any 2 into any natural number will give you 1? No. 2 into any natural number will not give you 1. So you will not have any element in your domain such that its image is 1. So it is not onto. But the same thing if you define a set of real numbers, then it is possible. Correct? If you take any y in R, there exists y by 2 also in R. Correct? Because R contains fractions. So y by 2 in R. So that f of y by 2 is, what is the definition of x? 2 into the element. So 2 into y by 2 is y. So y is onto. So for any element, if you are having over here y in the range, you will always find an element y by 2 in the domain such that its image is y. So this function is onto. Remember, to show that the function is onto, simple technique is take an element in your codomain or range and show that there exists an element x in the domain such that fx is equal to y. A 1, 1 function f from x to x is necessarily onto, and an onto function is necessarily 1, 1 for every finite set x. Remember, if you are having any finite set, then if a function is 1, 1, then it is onto. If the function is from the same set to itself, then it is, if it is 1, 1, it is onto, and if it is onto, then it is 1, 1. But for an infinite set, this might not be true, and this is the main difference between a finite and infinite set. This can be asked in objective questions. For example, say suppose if I am having a set A, which is a set of all 50 students of class 10th in a school. Suppose f is a function from a to n. N is the set of natural numbers defined as fx is equal to roll number of the student. F is 1, 1. Obviously. Why? Because every student will have some roll number and it will be different. Correct? But it might not be onto. Why? Because if suppose f is defined from a to n. So if I take any natural number, say if I am taking the natural number 200, then there might not be any student who is having the roll number 200 in the domain. So it is not onto. But suppose if I had taken the function f from a to a itself, that means here I have 50 students and in the range also I am having numbers only 1 to 50. Then in that case, the same function would prove to be onto. So what does that mean? That suppose if I am having a finite set, then if it is 1, 1, it is onto. If it is onto, it is 1, 1. But for an infinite set, this might not be always true. Now this example will help to understand the concept of 1, 1 and onto. You have to check whether following functions are 1, 1 and onto. First thing is to show any function f is 1, 1. Assume that f of x1 is equal to f of x2, and from that show that x1 is equal to x2. Suppose if you want to show a function is not 1, 1, then show that for some x1 and x2, if f of x1 is equal to f of x2, that does not imply that x1 and x2 are same. To show that a function is onto, take an element in the codomain. Remember, if I have a function f from x to y, x is the domain, y is called the codomain. So take an element in the codomain and show that there exists an element x in the domain so that f of x is equal to y. And to show it is not onto, take a number in the codomain and show that it does not have any preimage in the domain. First function f is from set of natural numbers n to n, given by fx is equal to x squared. This function is by default 1, 1. Why? Because you are having the set of natural numbers. So say if I have f of x1 is equal to f of x2, then x1 square is equal to x2 square, and that will imply that your x1 and x2 should be same. Correct? Because negative numbers are not there, only positive integers. It is not onto. Why? Because suppose I take an element, if I want to show it is not onto, over here one element is also sufficient. Say if I am taking 2 which belongs to the codomain n, then do you have any number x in the domain? That means do you have any natural number such that its square is equal to 2? No, there is no natural number whose square is equal to 2. So it is not onto. Second function, same function, but now it is from set of integers to set of integers. That means positive numbers, negative and 0. So again this now see this function is not 1, 1. Why? Because over here I can have f of 2 as 4 and f of minus 2 will also be equal to 4. So 4 is equal to 4. That does not imply that 2 and minus 2 are same. So I have shown that if f of x1 is equal to f of x2, it does not necessarily imply x1 and x2 are same. So it is not 1, 1. Now it is not onto by the same logic as we discussed previously. Suppose if I take an integer 2, then there is no integer whose square is equal to 2. Now set of real numbers. If the same function is from R to R, then this function is again not 1, 1. Same reason as we had previously, because R means Z is included. So you have say 4 is equal to 4 does not imply 2 is same as minus 2. It is not 1, 1. Now this function is also not onto. Why? Because see, suppose if I am having the value of fx as minus 1, that means I am taking an element minus 1 in the codomain. Correct? Then do I have square of any real number which is equal to minus 1? No. Correct? You know that you cannot have any real number whose square is minus 1. It will be then a complex number. So for R to R it is not onto. This is the example which can be given. Fourth one, suppose natural numbers f is from n to n given by fx is equal to x cube. This function is 1, 1. Again, because only positive numbers are included, so by default this function will be 1, 1. It is not onto. Same reason, suppose say if I am having 2. 2 is a natural number. Do I have cube of any other natural number whose cube is 2? No. So for 2 belongs to the codomain n, I cannot find any natural number in the domain such that fx is equal to 2. Now for z to z, same function fx is equal to x cube, it is 1, 1. Remember fx is equal to x square was not 1, 1, but fx is equal to x cube is 1, 1. The reason is you know that if I have the cube of minus 1, it will be minus 1 and cube of 1 will be 1. Same way if I am taking cube of minus 2, it is minus 8 and cube of 2 is 8. So both are different. So in this case it will be 1, 1. It is not onto. Same reason. Suppose if I take say any integer 2 in the codomain, can I get the cube of any other integer which is equal to 2? No. So it is not onto. Next example. Prove that the greatest integer function GIF f which is from R to R given by fx is equal to square bracket x is neither 1, 1 nor onto, where it denotes the greatest integer less than or equal to x. First thing is, I hope GIF function is clear. Suppose if I am having 5.6, which is the greatest integer less than or equal to it, it is 5. So 5.6 will also amount to 5 and 5.4 will also amount to 5. So greatest integer function denotes the greatest integer less than or equal to x. Now, first thing is, suppose if I am having, you can take any elements. I have taken 1.2, 1.6. Both of them belong to R. Both are real numbers. F of 1.2 is equal to F of 1.6. Just now as I told you, both will give a greatest integer function. So both will result into 1. So F of 1.2 is equal to F of 1.6. But is 1.2 equal to 1.6? No. So the function is not 1, 1. Correct? Second thing is we want to check for onto. Suppose if I take 1.2 belongs to R, the codomain, I want to see if there exists any real number x in the domain such that fx is equal to 1.2. Does it exist? No. Why? Because our function is denoted by greatest integer. So it will always give back the value of integer. So fx value 1.2 is not possible. Correct? So the function is not itself onto. So this function f, GIF function f, is neither 1, 1 nor onto. Next example is for the signum function. Remember, these type of functions are generally asked in the exams. So try to understand each of them. Show that the signum function f from R to R given by fx is equal to 1 if x is greater than 0, 0 if x equal to 0, and fx is minus 1 if x is less than 0. Now first of all we will check for 1, 1. So you have 1 and 2 belongs to R. F of 1 is equal to f of 2. Why? Because f of 1, that means your value of that x is greater than 0. So f of 1 will result into 1. F of 2, again 2 is greater than 0. So it will always give you the value 1. This is how our function is defined. Okay, if x is greater than 0, fx value is always 1. So f of 1 and f of 2 are same, which are 1. But 1 is not equal to 2. So f is not 1, 1. Now regarding onto. Now you can see that the range over here is minus 1, 0, 1. Only 3 values fx can take, which are minus 1, 0 and 1. Correct? The signum function's codomain is a set of all real numbers. Now remember, range will be the subset of codomain. Codomain means f is a function from R to R. So first R is called domain, second R is called codomain. Range means the values which fx can take. So in this case, fx can take only the values minus 1, 0 and 1. Now since the signum function only outputs were minus 1, 0, 1, there are infinitely many real numbers in the codomain, say 2, 3, 4, many numbers. R is the whole set of numbers. So except minus 1, 0, 1, remember, in the codomain there are many numbers, 2, 3, 4, 6, all the numbers which are not there in the range of this function. So which you will never get as fx. Therefore the signum function does not cover the entire codomain, and so it is not onto. For example, there is no value of x in the domain R for which fx equal to 2, as I said just now. For example, because the signum function has only the output values 1, 0, minus 1. Correct? So for any other value in the codomain, you can never find an x in the domain. Now in this example, let f be a function from n to n, and it is defined by f of n is equal to n plus 1 by 2 if n is odd, and is equal to n by 2 if n is even, for all natural numbers n. Check whether the function is bijective, means whether it is 1, 1 or 2. First case is, suppose you are having f of 1, 1 and 2 are natural numbers. What will be f of 1? F of 1, 1 is odd, so it is 1 plus 1 by 2, that is 1. F of 2, 2 is even, so the function is defined as n by 2, 2 by 2 is 1. So now f of 1 and f of 2 both are having the same values 1, but can you say 1 equal to 2? No. So f is not 1, 1, correct? Now for onto. For onto, let us take two cases. First case is when n is odd. N is odd means obviously it will be of some type 2k plus 1 type, because it is an odd number. Now there exists y belongs to codomain n. Remember, domain, codomain both are same, so I have written over here, let y is equal to some 4k plus 1. You can have any type of numbers in the codomain. So suppose 4k plus 1 is any number in the codomain. Then what will f of y be? F of y will be f of 4k plus 1. Correct? But 4k plus 1 means it is odd. So the function is, when the number is odd, the function is given by that number plus 1 by 2, means 4k plus 1 by 2. So that is equal to 2k plus 1. Obviously 2k plus 1 is our number in the domain. Why? Because in this case, in the domain, we are considering the odd numbers. Okay. So actually what I have shown is, there always for any number, any odd number n, there will always exist an y which is of the type 4k plus 1 in the codomain, such that your f of y will be an odd number. So we have shown that in this case f is onto. Second case, n is even. Try to understand. Second case, n is even, so n it will be of the form 2k. Correct? Now there exists some y is equal to 4k which belongs to the codomain. So now since y is of the type 4k, So that means your number is even. When the number is even, the function is defined by number by 2, n by 2 type, correct? So f of y will be f of 4k, which is 4k by 2, which is 2k. 2k means that are the numbers in our domain. We have taken even numbers. We are considering this case for even numbers. So for y is equal to 4k in the codomain, I will always have n number in the domain. So f is on 2. F is not 1 1, but f is on 2. So you can say f is not bijective. For bijective, it should be both 1 1 and on 2. Now next topic over here is composition of functions. Suppose f and g are two functions. F is a function from a to b, g is a function from b to c. Then the composition of f and g denoted by g of f is the function g of f from a to c, given by g of x is g of fx for every x belongs to a. Let us understand composition of functions with the help of an example. Find g of f and f of g. For f r to r, g r to r, fx is given by cos x and gx is given by 3x square. First thing is we will find g of f of x. By definition, it is equal to g of fx. So that is g of, what is fx? Cos x, g of cos x. So it is, what does the function g do? 3 into the number square. So 3 cos x square. So g of f of x is 3 cos square x. Now we find f of g. F of g will be f of gx. So f of 3x square. What does function f do? It takes a cos value. So it is cos of 3x square. Now remember, 3 cos square x is not equal to cos 3x square. Specifically, you can check for x equal to 0. When x is 0, you know cos 0 is 1. So 3 cos square x is 3. Cos 3x square is 1. 3 and 1 are not equal. G of f is not equal to f of g. So this also shows that it is not necessary that always g of f and f of g are equal. A function f from x to y is defined to be invertible if there exists a function g which is from y to x such that g of f is identity function on x and f of g is identity function on y. The function g is called the inverse of f and it is denoted by f inverse. Correct? So now if your g of f is ix and f of g is iy, then your function g is called inverse of f and f is said to be invertible. Thus, if f is invertible, then f must be 1 1 and onto, and conversely, if f is 1 1 and onto, then f must be invertible. Next example. Let f be from n to y and fx is a function defined as fx is equal to 4x plus 3, where y is the set of all natural numbers such that y is equal to 4x plus 3 for some x belongs to n. Show that f is invertible and find its inverse. Now, consider an element y of y, correct, of the codomain y. By the definition of y, it consists of elements of the type 4x plus 3. So y is equal to 4x plus 3 for some x in the domain n. So make x as the subject of formula. See, this is a technique. Whenever you want to find the inverse, just make x as the subject of the formula, correct? It will be very easy. So x is equal to y minus 3 by 4. So now based on this, I define a function g which is from y to n. Remember, I want to show g is the inverse of x. So now I am defining g from y to n, where g of y is equal to y minus 3 by 4. Now find g of f of x. G of f of x is g of fx. Fx is 4x plus 3. And when you apply the function g, what does it do? Y minus 3 by 4 means the number minus 3 by 4. 4x plus 3 minus 3 by 4, which is equal to x. Now find f of g of y. Remember, f of g will be of y because your function g is defined from y to n. So f of gy. So f of y minus 3 by 4. What does the function f do? F is 4x plus 3 means 4 into number plus 3. So 4 into y minus 3 by 4 plus 3. So it will give you y. So you have shown that g of f is the identity function on n and f of g is the identity function on y. So it implies that f is invertible and the g which we have defined is the inverse of f. Next example. Show that the function f which is from R to the set of all elements x belongs to R such that x is between minus 1 and 1. It is defined by fx is equal to x upon 1 plus mod x. X belongs to R is 1, 1 and on to. This is what we have to show. First thing is we will define what is the mod function. You might remember mod function fx means it gives minus x if x is less than 0 and it gives x if x is greater than or equal to 0. Like for example, mod 3 is 3, but mod of minus 3 is minus of minus 3, which is 3. Correct? So this is a definition of mod function. Now fx is equal to x upon, now see if x is less than 0, then what will be your value of mod x? Mod x will be minus x. So instead of mod x, put minus x. So your definition of function has changed to fx is equal to x upon 1 minus x if x is less than 0. And similarly, fx is equal to x upon 1 plus x if x is greater than or equal to 0. Because in this case, mod x is x. Now first part is for 1, 1. If x is less than 0, suppose fx is equal to fy. That means 1 upon 1 minus x is equal to y, x upon 1 minus x is equal to y upon 1 minus y. So when you simplify this, you will get x equal to y. And if x is greater than or equal to 0, again assume fx is equal to fy. So x upon 1 plus x is equal to y upon 1 plus y. So simplified, this will give you x is equal to y. So in both the case, we have shown that f is 1, 1. Now, in the second part, we need to show it is onto. Correct? So again, first case, let x is less than 0. Take any element y belongs to the codomain. So let y belongs to R. So y is equal to x upon 1 minus x implies that when you just simplify this, x is equal to y upon 1 plus y. Again, I am telling you, whenever you want to show this onto, try to convert it in the form of x. It will become very easy. So now, since your y belongs to, once again, since your y belongs to R, and this is how R is defined, it is a set of all functions which satisfy the above definition. So x upon 1 minus x in case x is less than 0. Simplified, this will give you x is equal to y upon 1 plus y. Let this be equation 1. Second case, if x is greater than or equal to 0, in this case, take an element y belongs to R and define y is equal to x upon 1 plus x. Try to define y as x upon 1 plus x. Make x as the subject of formula. This will give you x is equal to y upon 1 minus y. Correct? Now, your y belongs to the given set where x belongs to R, where that value of x is between minus 1 and 1. Hence, if y is minus 1, then by 1 it is not defined. Now see, over here, our element y, correct, which is in the codomain, it consists of elements of the type which are between minus 1 and 1. For example, if it is exactly minus 1, what will happen? From the first equation, when you put y minus 1, it will be minus 1 upon 0, so that anything upon 0 is not defined, so it will not be defined. Similarly, if you put the extreme value y equal to 1, then by equation 2, x will not be defined. Hence, for x belongs to R, it will be defined for all values of y, so f is onto. What does this mean? That we have shown that since for minus 1 and 1 it is not defined, it will be defined for all the values in between that. So our function is onto. We have taken y and we have shown that there exists some x in the domain for that y, and which satisfies the given condition. So f is onto. Next example. Let f be a function from R to R defined as fx is equal to 10x plus 7. Find the function g which is from R to R such that g of f is equal to f of g, which is the identity function. That means basically you have to find the inverse of f. Correct? So let us find the inverse of x where g is the inverse of x. Now let y is equal to fx is equal to 10x plus 7. This is given to us. Again, as I told you, what you have to do, make x as a subject of formula. So x will be equal to y minus 7 by 10. So now I can define a function g R to R such that g of y is y minus 7 by 10. Now check the conditions, find g of f and f of g. So g of fx is g of 10x plus 7, which is equal to x, and f of g is f of gy, f of y minus 7 by 10, which is equal to y. So we have shown in both the cases that f of g and g of f are the identity functions. Since it is from R to R, both are the identity functions. f is invertible and the inverse of f is given by our function g. Now some conceptual questions. Find the number of all onto functions from the set 1, 2, 3 to itself. Correct? The number of all onto functions from a set A which has 3 elements 1, 2 and 3 to itself will be 3 factorial, which is 6. Why? Now you can see over here from the diagram, as f is onto, what will happen? Every element in the codomain also has elements 1, 2 and 3. So every element of your codomain will have a unique pre-image from either 1, 2 and 3 of the domain. Correct? So the total, how do you define this? This will be the total number of permutations of the 3 elements. Correct? Because from every element 1, 2, 3 you can match it to every other element of the domain. So it will be nothing but the total number of possible arrangements which is given by permutation. So you know that the formula for permutation, correct, it will be 3 factorial. So in this case it will be 3 factorial. Now remember, if it is asked for any n number of elements, the answer would be n factorial. Okay. Similarly, next we try to find the number of all 1, 1 functions from set A to itself. Again, A has 3 elements. Here also the answer will be 6. Why? Because f is 1, 1 means every element of 1, 2, 3 will have a unique image from any of the elements of the codomain, but that also has elements 1, 2, 3. So the total number of permutations over here will also be 3 factorial, and it is shown, all the permutations are shown in the diagram. Again over here, the number of 1, 1 functions from set A, suppose if it has any n number of elements to itself, would be n factorial. So for both 1, 1 and onto, the answer is n factorial. In the previous video, we had discussed the types of relation. In this, we have discussed functions. So now let us try to take some extra examples based on them. Given a non-empty set X, consider Px, which is a set of all subsets of X. Define the relation R in Px as follows. For subsets A, B in Px, A is related to B if and only if A is a subset, proper subset of B. Now is this relation R an equivalence relation? Now let us try to understand this. First thing is, equivalence means we need to prove for reflexive. Now here it is given that it consists of, what are the members? Members are subsets, correct? It is defined on Px. Px is a set of all subsets. So now take any two subsets. Say if I take A will always be a subset of A, so it will always be reflexive. Now suppose if A is related to B, means A is a proper subset of B. Then does this imply B is a subset of A? No. So R is not symmetric. Now for transitive, if A is a proper subset of B, B is a proper subset of C, always A will be a proper subset of C. So A will be related to C. So it is transitive. So in short, we have shown that it is reflexive and transitive but not symmetric. So it is not an equivalence relation. Next example on relations. If R1 and R2 are equivalence relations in a set A, show that R1 intersection R2 is also an equivalence relation. Now see, first of all, since both R1 and R2 are equivalence relation, they will be reflexive, symmetric and transitive individually. So AA will belong to R1. Obviously AA will also belong to R2. So AA will belong to R1 intersection R2. So R1 intersection R2 is reflexive. Now for symmetric. Suppose if AB belongs to R1 intersection R2, means ordered pair AB belongs to R1 and it also belongs to R2. Now since R1 and R2 are individual equivalence relations, so they are symmetric. So if AB belongs to R1, BA will also belong to R1 because R1 is symmetric. AB belongs to R2, BA will belong to R2 because it is symmetric. So now BA will belong to R1 intersection R2, so R1 intersection R2 is symmetric. Similarly, let AB, BC belong to R1 intersection R2. This will imply AC will belong to R1 and also AC will belong to R2 because again individually R1 and R2 are equivalence, means they are also transitive. So AC ordered pair will belong to R1 intersection R2, hence it is transitive. So we have shown that R1 intersection R2 is an equivalence relation. Next example, let R be a relation on the set A of ordered pairs of positive integers defined by XY ordered pair is related to UV ordered pair if and only if xv is equal to yu. Show that it is an equivalence relation. Now see here, our relation is defined in the manner given above. So first thing, let us check for reflexive. So suppose xy is related to xy, correct? Then what will happen? The first and the fourth coordinate, that means xy will be equal to yx. That is always true. Xy you can always write as yx, so r will be reflexive, correct? So we have shown that always xy will be related to itself, xy, so r is reflexive. Now next, let xy be related to uv. This is given, we are assuming this. So what will this imply by definition? Xv will be equal to yu, correct? But yu you can write as uy and xv you can write as vx. So again, by definition of our relation, this will show that uv is related to xy, correct? So r is again symmetric. Similarly, let xy be related to uv and uv be related to some ab. Then by definition xv is equal to yu and ub is equal to va. But now suppose if I want to write xb, can I write it as x into, instead of b from the above equation, what is b? b is va upon u. So instead of b I am writing va upon u. So this will be xv into a upon u. But what is xv? It is yu. So this simplified as ya. So what we have shown is now xy is also related to ab. So the relation r is transitive. Hence r is an equivalence relation. Some objective questions. Let A have elements 1, 2 and 3. The number of relations containing 1, 2 and 1, 3 which are reflexive and symmetric but not transitive. How many such relations are possible? The answer is 1. Why is it 1? Because you want that the relations are reflexive and symmetric. Reflexive means 1, 1, 2, 2, 3, 3 should be there. Remember in the previous video we had discussed what is reflexive. AA type of pair belongs to it. Symmetric, if AB belongs to the relation, BA will belong to the relation. So here 1, 2 is there, 2, 1 is also there. 1, 3, since you need 1, 2 and 1, 3. So 2, 1 and 3, 1 should always be there. So now this is reflexive and symmetric. But why is it not transitive? Because 2, 3 does not belong to R. Correct? Why? Because you have 2, 1, you have 1, 3. So 2, 3 should also belong to R if it is transitive. But it does not belong to R. So the relation is not transitive. And actually if you check it out, this is the only one possible relation which is reflexive and symmetric but not transitive. Similarly, in the second case, suppose if A has elements 1, 2, 3, the number of equivalence relation containing 1 and 1, 2 ordered pair is how many? 2. What is the reason? Now see, first of all, the smallest equivalence relation containing 1, 2 will be, since you need it to be equivalence means 1, 1, 2, 2, 3, 3 should be there, reflexive. Symmetric because 1, 2 is there, 2, 1 should also be there. So 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. This is the smallest possibility. And this relation is also transitive. You can check it out. Very simple. 1, 2 is there, 2, 2 is there, 1, 2 is there. That means it is basically reflexive, symmetric and transitive. The only relation which is bigger than this relation and it is also equivalence relation, that is only possible for universal relation. Like universal relation means all the ordered pairs are included. So 1, 1, 2, 2, 3, 3, 1, 2 is there. So you will need 2, 1. Correct? Now I want a bigger relation than my given relation. So suppose if I am adding 1, 3, I should add 3, 1. If I am adding 2, 3, I should add 3, 2. Now if you check over here, it will always be transitive because all the ordered pairs you have included. And no other relation. Suppose if I take out 3, 2 from this set, from the second set which I have defined, what will happen? It will not remain symmetric because 2, 3 will be there but 3, 2 will not be there. So in short, only two possibilities are there for equivalence relation, and that is the smaller set and the universal relation. Okay, so if for these type of examples, you just need to think and give the answer. Students, we have discussed the first topic of class 12 maths, which is relations and functions. In the previous video, we had discussed relations and its types. In this video, we have seen functions and its type 1, 1 and on to functions. Do like and share the video and subscribe to the channel for maths of class 9, 10, 11 and now class 12.